Perfect. Welcome, everybody. Thanks for tuning in to today's seminar, where we have 3 talks by early career scientists presenting their work. And we'll do it as we always do, that we first listen to all 3 talks. And after that, we have a joint discussion and question and answer session. And we'll head off with Ann-Sofie Zinck from Delft University of Technology. And she's a PhD student using high-resolution satellite imagery and altimetry to obtain high-resolution basal melt rate of the Antarctic ice shelf. And with that, over to you, Ann-Sofie.
Thank you very much, Rebecca. So let me see if this, yes, it works. Perfect. So yes, as Rebecca nicely introduced me, my name is Ann-Sofie Zinck and I'm a PhD candidate at TU Delft. And today I want to talk about a high resolution approach to obtain basal melt rates of the Dotson Ice Shelf and reveal new melt patterns. And before I sort of start, I want to just make a small advertisement that what I'm presenting today is also currently under review in the cryosphere, so it's already available as a preprint. But if we now focus on the Dotson Ice Shelf, which we see on the satellite image to the right, then the Dotson Ice Shelf is located in the Amundsen Sea embayment of Antarctica marked with the red dot. And this is a region in Antarctica where warm circumpolar deep water reaches the ice shelf cavities, which then means that the ice shelves, they start to melt from below. And when they melt from below, they start to thin, and this can lead to a number of different processes, such as grounding line retreat, increased ice flow over the grounding line, and essentially put the stability of the ice shelves and their tributary glaciers at risk. And therefore, it's very important that we monitor such a parameter as the basal melt rate of the ice shelves. But how can we calculate the basal melt rate using remote sensing? Well, what we can do is that we, from remote sensing, can create or can get high resolution elevations or get surface elevations of the ice shelves. And if we have more surface elevations from different times, from different steps in time, we can generate elevation change maps from that. And with the elevation change, we can combine that with other data, such as the firn content and the velocity divergence. So basically how the ice flows, how it compresses and diverges, and the surface mass balance. And with those inputs, we can then calculate the basal melt rate of an ice shelf using remote sensing. And this has, for instance, been done by Adosumili et al., which we see here. And here we see a nice overview of all of Antarctica, where they have obtained 500-meter resolution basal melt rates of all of the ice shelves in Antarctica. And here we can see, for instance, in the Amundsen Sea sector, where the Dotson Ice Shelf is also located, we see in general higher basal melt rates here. So it's an area where all of the ice shelves are subject to basal melting. And what we also see here from this view, when we look at all of Antarctica together, is that, well, we see a spatial variability of the different ice shelves, and it looks like pretty high resolution, which, to be fair, it also is when we're talking about Antarctic-wide scale. But if we zoom into an ice shelf, such as the Dotson Ice Shelf, this is from another study, Gourmet et al., but also at a 500-meter resolution, we do see that it's not as smooth an image as when we look at all of Antarctica together. We still see spatial variability here, but it's not to the same, well, we can imagine that there might be features which we're not able to represent at a 500-meter resolution. And an analogy that I like to use is that of a window. So if I now tell you that here, it looks very pixelated, but it is an image of a window. And if you had a tennis ball and were to smash this window, and I just told you to throw a ball at it, well, right now, I'm not sure that many of us would know where to aim at. But if we had higher resolution, I'm pretty sure that now most of all would aim at the same spot on this window. And that analogy can sort of be used with ice shelves as well, because these cracks on this window, they serve as weak spots on the window, and in the same way, small scale features on ice shelves may serve as weak points on ice shelves, and thereby also have a role on the potential or on the stability or instability of an ice shelf. So therefore, it's important that we also study these small scale features on the ice shelves. But how do we obtain high resolution basal melt rates of the Dotson Ice Shelf? Well, I would like to introduce a method which we call BERGI, and that simply stands for basal melt rates using REMA and Google Earth Engine. So BERGI is a method where we, as mentioned, use REMA. That's the reference elevation model of Antarctica, and it has a lot of elevation strips at 2 meters spatial resolution. So that's extremely high resolution. But these strips, they are not properly co-registered. And for that, we use CryoSat2 to co-register the strip. And then we make use of the Google Earth Engine. And the Google Earth Engine allows us to process a lot of data really fast and really efficiently. And we don't need our own computer power to do so. Another good thing about the Google Earth Engine is also that a lot of the data, such as REMA, is already available in the Google Earth Engine data catalog. So we also don't need to download a lot of data, which makes it a really nice method, a really nice tool to use. And with BERGI, we are able to get the basal melt rates of the Dotson Ice Shelf at a 50-meter resolution, which we see here. And if we compare that to previous studies, so for instance, to the study as before from Gourmelen et al., in the middle, which is also a remote sensing based study, but it's a study that uses CryoSat2 data only, CryoSat2 data in SWOT mode. And then to the right, LADI, we have an ocean model study. So this is not remote sensing based, but it's from an ocean model. And the first point that I want to make is that the different products, they show similar large scale patterns. And that is such as this bigger main channel running along the entire length of the ice shelf, more or less, and that was already discovered by Gourmelen. But we see that also in LADI and in BERGI. Another thing that we see is this convergence zone just east of a pinning point, where we have high basal melt rates as well. That's also present in all 3 products. And then also this increased basal melting near the polar grounding zone. But if we then focus on some small scale features, then the different products, they start to differ. So zooming in on this box here, we now see a zoom in and below. And if I then mark this area here, then both in BERGI and in LADI, we see a smaller coastal channel, which is not present in the study by Gourmelen. So that really shows that BERGI is able to capture smaller scale features which coastal resolution products cannot capture. So that is really promising to see. Another thing that I want to focus on is this pinning point on the ice shelf. And if we now only look at BERGI and the pinning point again, then if we follow this arrow and follow the main channel in the direction of the arrow, then we see that this channel starts to form a wavy pattern after the pinning point. And we want to see, well, how that can be. So, well, the first thing that we do is that we plot both the surface elevation in red and also the basal melt rates here in black. And what we see is that in the vicinity of, and that's along the cross section, the gray line that we see on the top figure. And what we see from the right, where the pinning point starts, we have some surface undulations appearing that become bigger and bigger after the pinning point. And it's, well, when the ice flows over a pinning point, it makes sense that these undulations will form in the ice due to the, simply due to the ice flow over the pinning point. But what we also see is that in areas where the surface elevation is higher, so that means greater ice thickness, those are also areas where we have higher basal melt rates. And we want to, well, get a better image of why this is the case, and maybe also if the pinning point is, how this pinning point is influencing that. And if we then also look at LADI, so that's the ocean model study, and the square that I have marked here, if we zoom in on that, then this is the LADI model study. And the zoom in to the right shows the basal melt rate and the surface elevation. And the basal melt rate that we see here, we also see this wavy pattern. I should mention here that in Ladi we see it next, like sort of a bit next to the channel, and not in the channel as we see from the observations. But we can still compare this to what we observe. And what we also see is that there are these surface undulations appearing in the surface elevations. And if we then break the basal melt down to some simple terms, well, then basal melt can be approximated by two terms. One is the friction velocity, so that's how efficiently the heat is transported to the ice. And the other one is thermal forcing, so that is the heat available to melt the ice. And then to have a look at these two terms, which one is at play here in this area, then we see in green the friction velocity, and in the red colors we see the thermal forcing. And it's pretty clear to see that, well, the thermal forcing, depending on the quality of your screen, you might not even see a difference. And with the friction velocity, we clearly see a pattern that looks like the basal melt rate. And also, if we plot it as a function of the basal melt rate, then in green we see this clear correlation between the friction velocity and the basal melt rate, and no clear correlation between the thermal forcing and the basal melt rate in this area of the ice shelf. So what that means is that the meltwater plume simply is being squeezed down. It makes a convergence and converges like below the ice, where the ice goes deepest into the ocean. And that's why we then observe a lot of melting in this area where the surface elevation is greater, and thereby the ice is deeper, which is what we see in our study. So this really sort of makes us think about, okay, but what really, like, is this something which the pinning point is, like, how big of a role is the pinning point? And also, how may this be on other ice shelves? And could it be that the pathway of this channel was different if there was no pinning point here? And those are things that we discuss further in the paper, and I would recommend people that are interested to go look at that in the paper, because I will not go into detail about that here. But the take-home messages that I want to give from this presentation here is that basal melting also happens at a fine scale, and with Burgard we're really able to capture that, and we can already see how we are able to capture features with which products, of course, a resolution is not able to capture. The next thing is that ice shelf pinning points, they may impact the spatial basal melt variability, and that is something which we also really find interesting to study further in the future. And new observations can also easily be included in Burgard. So as I mentioned, we use the Google Earth engine, and when REMA 2 becomes available, which I hope it will in sort of the near future, then we can easily apply this to the updated, to the REMA 2 surface elevations, and then expand our study period. And also Burgard can easily be applied elsewhere to other ice shelves, and this is a method which is especially interesting for ice shelves that are melting, that show spatial variability, where we think that it's very important to understand some of these smaller scale features, and what so that would really be nice to also try to do this on other ice shelves, and not on ice shelves that are as boring as the Dotson, which is, to be fair, pretty boring because not much is happening here. And with that, I think I would like to say thank you, and both the method, the data, and the code can be found in the preprint, and so that's also the Burgard code and everything. So thank you very much.
Thank you, Ann-Sofie. It might be worth to send a link to the preprint in the chat if you have that.
Yes, I will do that.
Cool, perfect. Thank you. Looking forward to reading that. And with that, we are over to the second speaker, who is Stephen Franke from Tübingen University and AWI in Bremerhaven. And he is studying ice internal and ice bed processes using radio echo sounding data.
Yeah, thanks, Rebecca. I hope you can see and hear everything. Okay. Yeah, thanks for the invitation, and also thanks to and greetings to Palek, who's not here. So the overall question of my presentation is, or goes in the direction of how dynamic is the Greenland ice sheet. And what I mean with dynamics in this case is the dynamics of ice streams, and how ice streams, or how, for example, the ice stream configuration of Greenland may have looked in the past. So if we consider the image on the left, which are flow lines and the color-coded ice flow velocity of the Greenland ice sheet, the question is, how did that look maybe a few thousand years ago? And if it has been exactly like this or some sort of stable. And I also want to promote a manuscript. So a lot of the content that I'm showing here has been published a few months ago in December in 2022 for further reading. So a little introduction. So here on the image on the left, we see what I would call a typical ice stream. So we have a region of fast ice flow. And then very often we have upstream a region of convergent flow, so that the ice mass that is evacuated in the fast flow region is then resupplied to the ice stream. And what we also have very often further inland is that we have a region that separates the fast ice flow from the slower moving ice. And this is often referred to as a shear zone or a shear margin. And then on the image on the right, we have the ice surface flow velocity of Greenland and Antarctica derived from satellite data. And here in the color code, for example, the blue and the purple colors indicate high flow velocities and sort of mark the locations where we have ice streams. And this is a very nice data if we want to see what is going on at the moment. But unfortunately, this data does go back maybe around 50 years ago, which is a relatively short time span to see actual changes in ice stream configurations. The second type of information that is available are the landforms that ice flow leaves behind at the glacier beds. And here, for example, we see on the left a reconstruction for the ice stream activity of the Laurentide ice sheet, which has been performed on the basis of these landforms. And on the right, we have satellite images where we clearly can see the traces that ice flow leaves behind. And we can here even separate two types or two stages of ice stream activity. So at some point, an ice stream was flowing in this direction. And then at a later subsequent stage, the whole system reconfigured and an ice stream was flowing here to the right. But there's a big problem if we want to go back in time and see how ice stream configurations were at still glaciated regions, like the Greenland ice sheet, for example, because the satellite data doesn't go far enough back in time. And we are still not really able to image the bed of ice bodies in such a high resolution and extension as, for example, in this satellite image here on the right. So one possibility where we could think about bridging this observation gap is the fact that ice flow leaves, or especially focused and localized ice flow, leaves traces of deformation inside of the ice. And then we have radar data, ice penetrating radar data that enables us to visualize these traces of deformations. So here in the upper image, we have again the ice surface flow velocity of Greenland, and we can see the several 100 kilometers long northeast Greenland ice stream. And in the lower image, we have a radiogram that is cross-cutting this ice stream at a certain location. And what becomes very apparent are these two, or the set of two times of these vertical white lines. And they actually represent zones or stripes of low reflectivity. And these are linked to internal deformation. So these are caused due to short wavelength faults and due to processing reasons of the radar data, and also geometrical issues in the acquisition. We have these low reflectivity zones. And if we have a look on where these zones happen in the ice stream setting, we see that they are related to the shear margins of this ice stream. And we can see this all over the place for NIGIS, so in the downstream region, but also very far upstream, very close to the ice divide. And because of these observations, we consider this signature in the radar data as a or as a clear marker for ice flow activity, or at least for this style of ice stream activity. So the very simple idea in this project was that we have a lookout for this signature that we see at NIGIS in the radar data that is available in Greenland. With the idea that if this signature appears in a region where we have no present-day ice stream, we have good reasons to assume that there has been an ice stream in the past if these structures are preserved. So we had a look at a lot of radar data in Greenland, in particular from Operation Icebridge, but also from radar data from Alfred Wegener Institute. And at the end, we could identify a handful of radargrams where we can find either almost exactly these features or features that are very similar. And we're going to have a look a bit in detail what that looks like. So here in panel C in the middle, we see 3 radargrams that are parallel to each other. And these are located at the position where we have this little arrow and the C, which is here in the velocity map. And we see that there's, at the moment, at least no ice stream as we can see here at NIGIS, for example. We see 2 times this special shear margin reflectivity pattern, and it appears in a very systematic way. A little bit further upstream, over here, we also find a similar feature, but we kind of only see one of them and not 2. So there we have a little bit of a different situation. And just for comparison again, on the bottom, we see the radar signature of NIGIS, and in the upper part, the one in the northern region. This is a comparison on a bit more detailed scale. So on the left, we have again a radargram in the what we like to call the passive setting, so the no NIGIS style present-day ice stream setting. And on the right, we have again a radargram cross-cutting through NIGIS. And next to these 2 times vertical low reflectivity zones, we also find additional similarities. For example, in the region in between of these 2 signatures, where we have relatively clear internal layers, and they also show this buckle fold style of folding or of compression. And another similarity is that at the edges or at the margins from the shear margin signature, we find these downward sloping internal layers. Yeah, and they are apparent on the right as well as on the left image. So what we take from this are basically 2 things. So we are very sure that these deformation patterns in the active ice stream region are extremely strong linked to the activity of the ice stream. So we can say whatever caused the features on the right might be also the reason to whatever caused the features on the left image, which gives us reason that to say that in this region, north of NIGIS, we had a second NIGIS style ice stream, which is not there at the moment. And the other thing is that if we agree that NIGIS ice flow is causing these deformation patterns, and if we then have a look at internal layer that is resembling the age of the last glacial to Holocene transition, we can say that the deactivation or the shutdown of this ice stream cannot be older as the layer that is kind of intersecting with these internal features, which gives us the information that this ice stream or this paleo ice stream did activate at least at some point in the Holocene, but not older, but not longer time ago. And this is now a map where we mapped all of these features that we could find, so the shear margin features. And here it's plotted on the ice surface flow velocity and on the gradient of the ice surface flow velocity on a logarithmic scale. And we see that in the downstream part, we really have this pairwise systematic pattern. They are arranged in a, let's say, in a width of 15 or 10 to 15 kilometers. And this gives us also an idea about the shape or the geometry of this former ice stream. In the upstream part, we had what I was mentioning, this, I wouldn't call it an issue, but this, this finding that we only see one of these shear margin signatures in the radar data. The second thing I want to highlight is on the image on the right, where we have resolved the, let's say, the ice flow velocity gradient on a very fine scale. We see this very little or very small signal in the flow velocity gradient, which is somehow, or which coincides in the upstream part with the location of these reflectivity patterns, so with the former shear margins maybe. And this is something that we that is maybe something for the discussion, because I think there are many opinions of what this could be, and we are also not really really sure about this. So in summary, or we could summarize all of this in a sort of a three-stage process. So at some point we had an ice stream that is very similar to Negus, but located much further north of Negus, that created these deformation patterns that we can make visible in the radar data. And then at some point this ice stream shut down because we don't see it at the moment in the ice surface flow velocity, but these features remained, which gave us the possibility to identify them. And then over time we have more and more accumulation on the surface, which compresses the whole ice column and reduces a bit the amplitude of these short wavelength folds. This is again a sort of a summary map. The orange arrow here is approximately the location where we reconstructed this ice stream. It depends on many different things where exactly this ice stream was been active, but must have been about in this region. And the fact that there was in the past an ice stream that is very similar to Negus but is not there at the moment gives us the chance to learn a lot, of course, about the ice sheet dynamics of Greenland. For example, on the topic of temporal variability, because apparently these ice streams are not, or this ice stream type is not unique, and it maybe comes and goes in relatively short timescales. The second thing, which is which contains a bit more interpretation, is that if we combine the Holocene deactivation of this paleo ice stream with some other research that is not published at the moment, where we have good or where we find indications that the upstream part of Negus is actually also relatively young, so 2,000 to 4,000 years old, we could think about some sort of switching mechanism, which may be, for example, related to a change in the ice sheet geometry, that something shut down here at some point and possibly reactivated or activated Negus in the upstream part. And But this second appearance of this style of ice streams also enables us is to rethink all of the theories that are out there that try to explain the existence of negids, for example, like the theory of extremely high heat flux at the base, which is possibly explained by a geothermal hotspot, and things like this. And then, as I mentioned, we have our gradient in the ice surface flow velocity. And for us, there are two types of explanations. So, for example, it could mean that the ice stream deactivated much more recently, and this is sort of some sort of remnant feature. Or maybe the other way around, that this is an indication for some sort of reactivation. Yeah, but I also would like to hear your thoughts on this. And yeah, that's everything I wanted to show. Thank you.
That's pretty amazing. Thank you, Stephen. It might be worth for you as well to put the link to the paper in the chat if you want.
Okay.
And we'll come back to questions later on. Thank you. Next one up, we have Clara, who is a postdoc at in Université Grenoble, and she's interested in large-scale modeling of ice-ocean interactions and focusing on basal melting in Antarctica right now. And Clara is also part of the EGU Cryosphere early career scientist team since 2016, which is pretty amazing, Clara. And with that, I would say over to you.
Okay, thank you very much. So pretty amazing. It just shows I'm a bit old, maybe. Anyway, so thank you. I'm not used to this laser pointer. Sorry, I want to put away the videos. Oops. Oops, better. Okay, sorry. So yeah, thank you. So I first want to thank again Rebecca and Tavi and everyone who organizes this IGS seminar series for having me here. So I also want to present a paper which has been accepted like for Stephen in December 2022. So it was the small Christmas present of the year. And it is a very long paper, so I want to give here the main results so that you maybe don't have to read everything and you know where to look for, what to look for. So very good that Ann-Sofie already introduced ice shelves and why they're important, so I don't have to go too much into details here, but here is a small recap. So ice shelves are the floating ice tongues at the margin of the Antarctic ice sheet, and they buttress the ice flow from the grounded ice sheet to the ocean. And this way they moderate the pace of the mass loss from the ground into the ocean and therefore the pace of sea level rise. And currently with climate change, the ocean is getting warmer and also the circulation is changing, and therefore warmer ocean water is getting or is touching underneath the ice shelves and leading to melt and thinning, so that there is less buttressing of the ice flow from the grounded ice sheet to the ocean, and therefore sea level rise can get faster and is getting faster. So basal melt is important, but we still have the problem of representing basal melt in ice sheet and ocean models. So as I said, ice sheet models need information about this melt to force the evolution of the Antarctic ice sheet, and therefore the Antarctic contribution to sea level rise. At the same time, ocean models also need this information because the melt in this cavity below the ice shelf affects the water in front of it. But typically, at the moment, the subshelf cavities are not resolved in ocean or coupled climate models, and so the link between the open ocean and the ocean ice sheet interface is currently missing. So this is not a new problem, and basal melt parametrization to bridge this gap have been developed in the past decades. And these parametrization, what they do is that they bridge the gap between the ocean temperature and salinity in front of the ice shelf, as given, for example, from observations and models without cavities, and the melt rates at the base of the ice shelves. But here again, we're still not near to the solution because evaluating this parametrization remains challenging. So the most natural way would be to do this with observations. And as we saw from Ann-Sofie, they are even like satellite melt estimates are getting better and better, but still they assume quite some things, so they're uncertain. And the main limitation is that we need also these the ocean temperature and salinity observations in situ in front of the ice shelves, and these cannot be retrieved from space, so ships have to go there. And therefore, we only have a few observations at some points in space and time, which is maybe not enough to generalize over whole Antarctica. Another solution is to use models. So this was done, for example, in 2019. There was an assessment and tuning made in an idealized couple ocean ice sheet model simulation. But this was an idealized geometry of one ice shelf. And then when applied on the circumantarctic level, it was shown that it was not diverse enough to only tune on one ice shelf because empirical corrections were needed. So we thought we build upon this idea, but we go for circumantarctic instead of only one ice shelf. And so our approach is to use circumantarctic cavity resolving ocean simulations as a virtual reality where we know everything to assess and retune the existing parametrization, this time really specifically for circumantarctic applications. So what does circumantarctic cavity resolving ocean simulation mean in our case? So we had an ensemble of 4 global ocean simulations done with the ocean model NEMO. And these simulations were conducted for another project, but they were there. So that's what we took. And they are resolved on a 1/4 degree grid. And in total, they represent 127 simulation years, which represent varying condition between 1980 and 2018. So it's not a projection of 127 years, it's just a total, an ensemble. And in this resolution, 35 cavities are resolved, which means the ocean circulation in the cavity and the basal melt is resolved. And these 35 are the 35 shown here in white on this map. And basically what this simulation gives is the ocean temperature and salinity in front of the ice shelf as we need as input for the parametrizations. We process them to make profiles averaged over a given domain in front of the ice shelf. And then the simulation also gives these basal melt rates so that we have our reference to compare to. And then we can put our parametrization in between and then see if what comes out compares well to what NEMO does. So in the first step, we retune the parametrization, this time for a circumantarctic approach. And what I mean by tuning is that we minimize the root mean squared error between the parametrized and the reference yearly integrated melt on the ice shelf level, which means that we take the ocean temperature and salinity from NEMO, we put it in the parametrization. This gives us computed melt rates, and then we compare to the target melt rates. But by comparing, we really don't take it at each grid cell, but we take one integrated melt for each ice shelf, and we do this yearly and not monthly. Okay, but tuning and evaluation also might depend on what we use for tuning and what we use for evaluation. So instead of just tuning on one part and evaluating on the other part, we do cross-validations over time and ice shelves, which means that we divide the data set into 35 ice shelves and into 13 blocks of 10 years. This is to avoid autocorrelation if we do it year by year. And then for the cross-validation over time, we tune over 12 blocks of time, evaluate on the 13th, and then we reiterate this 13 times until every time block was left out of tuning once. We do the same for the ice shelves, so we tune on 34 ice shelves, evaluate on 1, and then we do this 35 times until every ice shelf was left out of tuning once. So this is the methodology of the assessment. Then what do we assess? So which parametrizations? So there are different families. For example, there are the simple parametrizations that assume that the melt rate is a linear quadratic function of the thermal forcing, where the thermal forcing is the difference between the water temperature and the freezing temperature. And then the quadratic parameterization takes into account a slope. So we also test different slopes, either a constant over all of Antarctica, a slope for each ice shelf, or a slope at the grid cell level. Then we look at the plume parameterization, which assumes the formation of a buoyant plume at the grounding line, which then rises along the ice-ocean interface. We look at the box model, also known as PICO, which divides the overturning circulation in the cavity into boxes. And then we look at PICO, which is a combination between the plume and the PICO model. So in the paper, for those who have already seen it, there are a lot of dots. We tested a lot of variations also for the plume box and PICO. Here I will only show 1 point. This is just to make it a bit easier for the presentation, and the main conclusion remained the same. And so the first thing we assess is how good the parameterization performed depending on what temperature and salinity they got. So one test will be using temperature and salinity averaged within 50 kilometers in front of the ice shelf on the continental shelf. And one will be using offshore temperature and salinity, which means off the continental shelf in vicinity of the ice shelf. And how we assess this is by looking at the root mean squared error over the left out blocks of the cross validation. So always these blocks that I showed were evaluation before. And now we look at the integrated melt. So this was the quantity that was tuned to. And these are the results. And so the main takeaway here is that if you use offshore input, the RMSE will be slightly larger, or actually quite larger than using temperature and salinity nearer to the ice shelf front. Then second, you can see that the cross-validation over time leads to a lower RMSE than the cross-validation over ice shelf, which means that the parameterization can generalize better to time blocks it has not seen during tuning than ice shelves it has not seen during tuning, which again confirms that it's maybe not wise to only use one ice shelf for tuning. And if we want to decide which is best in this context, for the 50 kilometer input, it's the quadratic using a constant Antarctic slope or a local slope, or the plume parameterization. And for the offshore input, the RMC is higher for all and they're quite similar. But if we want to decide on some, we could say that the boxes and the PICOP and maybe the quadratic with the cavity slope have the comparably lower RMSE. But then for ice sheet modelers, it's not only the integrated melt that's important, but the spatial patterns. And I forgot, yeah, sorry. So as I said, the RMSE is lowest for 50 kilometer input. So in the next slides, I will only discuss results using this input. So we looked at also spatial patterns, and to do so, we looked at some maps. Here I show 3 famous ice shelves. So the 2 largest, which are Filch-Neroni and Ross ice shelves, and the Pine Island ice shelf, which is in the Amundsen Sea and is melting quite fast at the moment. And this is the reference. And these are how the parametrization do it. And I won't go into each panel in detail. The most important I want to take away from this is that you, at a first glance, you don't see any parametrization doing the perfect job. And at a second glance, you sometimes don't even see a parametrization doing a good job. So a lot of the patterns are not represented well by the parametrizations. This is what the eye says. We also wanted to have a quantification. So we looked at the metric, which is the mean melt near the grounding line. So it's again the melt near the grounding line. And again, we look at the root mean squared error. And these are the results. And we can see that the constant Antarctic slope, quadratic, and the plume again have low RMSE, but then, for example, the quadratic with the local slope has very high RMSE. This is because it actually really overestimates the melt there. So if we want to decide on something, it seems that the best compromise is to use a quadratic parameterization using an Antarctic slope or the plume parameterization. Also in our paper, which is very long, for those who are interested more in the technical details, we provide the best estimate parameters that are tuned on the whole data set, in opposite to what was done in the cross-validation. And then we give also uncertainty ranges around the parameters, because we showed that it depends on the tuning. Yeah, just to have some estimates of the uncertainty. And here I put again the title and where you can find it. And if you want to play around with the parameterization, I coded them all in Python, and I did a small Python package, so you are welcome to check it out. So as a summary, the main recommendation you should take away from this paper or this talk is that the continental shelf circulation matters. So better performances are there when using hydrographic profiles averaged over the continental shelf instead of away from it. You can keep it simple or go for a complex one. So either the quadratic parameterization using the constant Antarctic slope or the plume parameterization yield the best compromise if we look at the integrated melt and the melting at the grounding line. If you have no choice but using offshore input, then the comparably lower RMSE is reached with the box and pico parameterizations. And I think the most important takeaway here, which shows that there's still a lot of work to do, is that circumantarctic tuning is tricky. Most parameterizations do not generalize well to ice shelves not seen during tuning, and so tuning on the circumantarctic level will bring some uncertainties. So if possible, use the uncertainty ranges around the parameters that I provide, or go back to local temperature corrections. This is still to be discussed for the future. Here I put the QR code if you want to get to the paper. Also, it has just the same title as this presentation. It's in the cryosphere. And yeah, and that's it for the scientific part of the talk. And then I have two advertisement slides. So one is that we are hiring in Grenoble if you're interested. We are looking for a postdoc for 2 times 18 months on the modeling of icebergs in the ocean model NEMO. This would be in the H2020 project Ocean Ice. And you can scan the QR code or just take this link, which will bring you to more description and who to contact and so on. And then Rebecca also wanted me to advertise the cryo hackathon, which will take place not this weekend, but the weekend after, from the 17th to the 19th of February. And it will be, yeah, just a hackathon playing with data and so on. So you are welcome to register at the link below. So that's it from me, and I thank you for your attention.
Thank you, Clara, for the advertisement and for your talk. Sounds like a really good toolbox that you created with lots of information. Thank you. Thank you to all the three speakers. And I think we'll open the Q&A session now. So the easiest way, and the way we normally do it, is that you raise your hand, the virtual hand in Zoom, or you just say in the chat that you have a question. And maybe I can start while others are starting to type. And I have a question for Stephen. So you've done this analysis for Greenland. Have you looked at most of the data from Greenland, or do you think there are more areas to explore? And if you say you've covered most of Greenland, are you thinking of doing the same for Antarctica?
Yeah, I have to admit it was, I mean, it was not a analytical search through the data. Yeah, but I mean, we're still pretty sure that this is the only extreme example where we see this type of signature in this systematic way. And for Antarctica, I mean, the problem is in Antarctica, everything is so topography predefined that I guess it's also much more unlikely that an ice stream like Nigis could form. But yeah, I mean, of course, it makes sense to scan Antarctic metadata for that also. Yeah.
thank you. I think we have a question from Roger.
Yes, I do have. First of all, thanks to all three speakers. Congratulations on pushing papers out. It's good to see. I have a question for Ann-Sofie. Actually, I've got a question and an apology, because it was me that joined a little bit late and I didn't unmute myself, and it was me laughing in the background, but I was laughing at your picture of the broken window and wondering how you managed to get an experiment like that through the university's health and safety people. Well done. Really just a really simple question. You showed us that nice picture of the surface topography against your basal melting picture, you know, one red line, one black line. What's the uncertainty bounds on those observations? How real are those little peaks and so on? And there are other questions to talk about the Fresnel zones and the spatial resolution of the data that you're using and so on.
Yeah, so for the surface elevation, that is originally at a 2 meter spatial resolution, which we then, well, after our co-registration, we use a 10 meter resolution, and then for this it's a 50 meter resolution. And I would say that the surface undulations which we observe, they are definitely there. And then you can, and what we observe from the basal melt rates, well, of course it would be very nice with some in situ measurements, but since what we find is also being supported by a model study which does not use the exact same data as we do think that there is something there, but it's definitely something to look more into, and where in situ measurements would be key to do this. Yeah.
Mm-hmm. Sure. Yeah, I was just wondering what sort of, the classic question: have you put uncertainty bounds on those points? Yeah, the one we ask everybody.
What we have done is that we have to justify the resolution, the 50 meter resolution which our basal melt rates are at, is that we perform a sensitivity experiment, which I did not describe at all here. So we test various resolutions, and then what we see is also that the highest resolutions, they correlate with the highest basal melt rates. In this experiment, that's still, well, it's I don't exactly remember the numbers, but it's within, I would say 10% or something. So it doesn't really change the pattern, so to say. So we're pretty confident about the pattern which we observe.
Sure. Smashing. Thanks very much. That's great.
You're welcome.
Thank you, Roger and Ann-Sofie. We have questions from Roland.
Hi. Well, thank you all for 3 very interesting talks. I wanted to follow up something that Stephen was commenting with regard to Antarctica. I would have thought it would be interesting to look for these sort of features in the Cycle Coast ice streams, because there's a lot of other evidence for ice stream stagnation, and it would be very interesting to see if one could put some sort of time frame on that. That's an area where the geographical control is A, not so obvious, and B, the variability is very clear.
Yeah, I mean, so the manuscript that I showed at the beginning is basically composed of 2 parts. So the one thing is this shear margin story, and the other thing is something that has been observed in the Cycle Coast as well, are these cylindrical folds that you see in a lot of places, and which are definitely also ice stream related. And yeah, and of course, and I agree, the big task is to find some sort of way of dating this. And yeah, that's my comment.
Okay, cool. Thank you, you two. Okay. Clara, do you want to comment on, I saw you just answered Natalie's question. Do you want to comment on that? Because people, not everybody can read the chat, especially like people on Facebook.
Okay, yeah, I can. Good that I written it up.
Sorry, yeah.
No, it's perfect. I can remember. So Natalie was asking if I tried using ocean profiles obtained from inside the cavities, for example, through boreholes. There are not many of them, but maybe that would be interesting. And I answered that that for tuning, we were really looking for diversity. So again, if it's not much, that did not, like, we were afraid that it would not help. And also our parameterization are really targeting models that do not see anything of the cavity. So comparing to what is in the borehole might not fit this purpose in this case. But I think having boreholes is still super interesting to really look at the melt happening at the ocean ice interface when we don't have to mimic all the circulation that goes with it. And so more observations is always good to understand what is happening there.
Okay, thank you.
Actually, I have one question also, if I may.
Yeah, of course.
For Ann-Sofie. So again, yeah, more observations is always good. And I was just wondering, so you said this can be applied to other ice shelves. So could this become at some point a circumantarctic product? Like, how confident are you? And how big are the uncertainties? Have you estimated them somehow?
Yeah, so if it can become a circumpolar study, well, the first thing is that the REMA strips which I use, they cover more or less all of Antarctica, but in terms of like the two bigger ice shelves, there are not that many repeat coverages, which I need to make thinning rates. So that's a bit of the thing. The other thing is also that even though I'm using the Google Earth engine, it is still a lot of data because I have to process a lot of data locally also, well, like Cryo-2 and that kind of stuff. So what we will do is probably focus on some of the key ice shelf, because I don't think we will learn much more from the bigger ice shelf having it at a higher resolution. So the focus will more be on ice shelves in the Amundsen-Bellinghausen Sea embayment. Yes, and when it comes to the uncertainty, well, we did a sensitivity study assuming that so we do all of our calculations in a Lagrangian framework, so following the ice parcel, and we believe that that is one of the key one of the main contributors to the uncertainty of the final product. And what we do is that we do make a sensitivity experiment, making like a false displacement of some elevation maps to see at what resolution does this error cancel out. And so we don't give an exact number of the uncertainty, but we more give it. So yeah, it's more that way we do it, because it's difficult to give an exact number of the uncertainty when there's so many different inputs and so much different data. Yeah.
Thanks.
Thank you, you two. And we have another question from Roger for Stephen.
Yeah, thanks very much, Rebecca. Thank you again, Stephen. I guess it's a mixture of ice physics and radar propagation I'm asking about. I wonder how long you think these vertical blank zones in the radargrams actually persist. What causes them in terms of what the radar doesn't have to reflect from, and how long they might persist after the original active formation of them on the margins of an ice stream has stopped.
Thanks. Good question. So there's a nice paper from Niklas Holschuh from 2014, and he's actually summarizing, I think, 3 reasons why we have these low reflectivity features. So it's data stacking from inclined reflectors. It's also the aperture of the whole radar system on acquisition, and then also the way of processing it, which also has its limitations. But I think in terms of, either these short wavelength folds are flattened out at some point, or the ice becomes, or so much time passes that the ice melts away. I mean, I think these would be two reasons how these features can disappear. Or you have some sort of extension to flatten the folds, which I think is maybe unlikely to think in an ice.
I was as much thinking about the blank zones, because there were quite a few others, much less prominent, but there were quite a few others in your radargram, and
yeah,
you know, why were they perhaps not an indication of an even older flow pattern in those ice streams? It's a really interesting project. So thanks very much for telling us about it.
Yeah, sure.
Okay, nice. Do we have any last minute questions? There is one for Clara. Oh, yeah. Let's do travel first. Are you able to predict future sea level rise caused by melting of Antarctic ice shelves?
So what I did helps too, but it's a big thing. So so first of all, the melting of Antarctic ice shelf itself does not lead to sea level rise because it's already floating. And then if it's melting and then more ground ice gets into the ocean, so this is rather modeled with ice sheet models that really can resolve all the equations that drive how the ice sheet will change. And so I'm just giving one tool to see how the ocean affects the ice sheet, but then we also need to know how the atmosphere, what is happening below, and so on. So that's other people doing this.
Okay, thank you. And Roland?
Hi, thank you. I had a question for Ann-Sofie. I realize that I'm not understanding how such high resolution results come out, because the very fine scale structure in the surface elevations on the ice shelf it's not obvious to me how that translates into being able to work out melt rates, because the system is not going to be in exact local hydrostatic equilibrium at the very fine scale. Could you comment on the relevant distance scales?
Yes, so of course there can be some bridging stresses acting over channels and that kind of stuff. We did not, well, we do take, what we do in our study is that in the vicinity of the grounding line, we do a gradual adjustment to not assume direct hydrostatic equilibrium at the grounding line. But of course, otherwise we assume hydrostatic equilibrium elsewhere on the ice shelf. The exact impact that has on the product, I have to say I'm not entirely sure of that. I do think that the patterns if we don't look at the actual numbers but look at the spatial variability, I think that that's what's more key in our product than the actual numbers and or magnitudes themselves. And I do think that those are still valid, but it's not something that we've looked further into in this study.
Okay, thank you. Just to point out, we have a pinning point. You typically get quite serious rumples in the surface, which obviously are not, this is grounded and not constrained by hydrostatic equilibrium. And those rumples are going to be carried away downstream, and there's going to be some time scale for those to evolve to being, might as well say, for those to evolve away to hydrostatic equilibrium downstream of that is going to take some time. And I mean, the simple example I always like to use for this is when Captain Scott directed those cairns on the Ross Ice Shelf. They were a couple of meters high. They did not reflect a tens of meters variation in the ice thickness of those locations. So one has to be quite careful about fine scale features, but I'm talking about tens of meters, and one could actually calculate what the both elastic and more technically the viscoelastic response of these bumps that you created at the pinning point, so how they should dissipate and how the system should return to hydrostatic equilibrium. But it's not obvious that you can use this at a very fine scale. That was just my question. What's the relevant scale?
Yeah, well, we also provide our product at a 250 meter resolution, and the conclusions, they do not change. So I think that also supports it.
Thank you.
Looks a bit like the discussion can go on forever, which is really nice. Thank you all for the questions and the answers. And I think it's time that we say thank you to all three speakers again. Thank you so much for 3 amazing talks. And with that, I think it's time to close the seminar and see you all for next week's talk.
Can I just say that next week's seminar is Akiko Saki from Nagoya University talking about high mountain Asia glacier inventory.
Cool. See you next week. Thank you to all.
Thank you. Thank you all the speakers, and thank you, Rebecca.
Bye.